I'm Louis Kauffman. I'm a professor of mathematics at the University of Illinois, Chicago. I study things like this, and I study topology, and I enjoy going to cybernetics meetings, and that's my short introduction. This is a workshop about the theme of reflexivity. Let me begin by just using my slides a little bit. On this first slide, I haven't defined reflexivity. We'll try. But I've given one of my favorite examples of speaking reflexively, the quote by Heinz von Forster, I am the observed link between myself and observing myself. And some people resonate to that kind of speech, and others might find it a bit cryptic. Because at this level, what one is looking at is how thought thinks about thought, or how thought relates to itself, and how that's related to one's sense of self. If you're a mathematician, you have a tendency to turn such things into equations in your mind, and I've written one that I find illuminating over on the right. If you were to take a box around it to mean observed, and two things next to one another as meaning a link between, then the equation on the right is a diagrammatic translation of the sentence on the left. It says I am equal to observed, the box around it, link between the juxtaposition I and observing I. But then, once it's put in that form, it becomes a kind of a resonant chamber, or a recursion, or a feedback out of time. And you can think about it that way. So that's one of the ways in which we're going to play with things here is that kind of translation back and forth. But then, on the other hand, one has this matter, which very well-known Pogo cartoon. The porcupine says, Pogo, the beauty of the forest primeval gets me in the heart. It gets me in the feet, porcupine. It is hard walking on this stuff. We have met the enemy, and he is us. And this is the large-scale reflexivity of our actions in the world. Of course, we're all thinking about that. But this talk, unless you push me or unless you want to bring up things having to do with current events, and I'd be happy if you did, is going to be a bit abstract, because I'm talking about the structure of reflexivity in language and the structure of reflexivity in mathematics. So, on the other hand, let's talk about it a little bit textually. So I want to read this to you. Reflexive is a term that refers to the presence of a relationship between an entity and itself. One can be aware of one's own thoughts. An organism produces itself through its own action and its own productions. A market or a system of finance is composed of actions and individuals, and the actions of those individuals influence the market, just as the global information from the market influences the actions of the individuals. Here it is the self-relations of the market through its own structure and the structure of its individuals that moves its evolution forward. Nowhere is there a way to cut an individual participant from the market effectively and make him into an objective observer. His action in the market is concomitant with his being reflexively linked with that market. It's just so for theorists of the market, for their theories, if communicated, become part of the action and the decision-making. Social systems partake of the same reflexivity, and so does apparently objective science and mathematics. In order to see the reflexivity of the practice of physical science or mathematics, one must leave the idea of an objective domain of investigation in brackets and see the enterprise as a wide-ranging conversation among a group of people. And then at once, the process is seen to be a reflexive interaction among the members of the group. Mathematical results, like all technical inventions, have a certain stability over time that gives them an air of permanence, but the process that produces these novelties is every bit as fraught with circularity and mutual influence as any other conversation or social interaction. In an observing system, what is observed is not distinct from the system itself, nor can one make a complete separation between the observer and the observed. The observer and the observed stand together in a coalescence of perception. From the stance of the observing system, all objects are non-local, depending upon the presence of the system as a whole. It is within that paradigm that these models begin to live, act, and enter into conversation with us. I won't read that for a moment, but that's the general point of view that I'm working in here. But most of the examples will be taken from very elementary mathematics. The theme is very general, and it applies to all our actions in the world. This is a reflexive statement of George Spencer Brown that I particularly like. We take the form of distinction for the form as an answer to the question, what is form? Where the form re-enters its own indicational space. I said before that I was going to play with mathematics and mathematical metaphors, and you'll see, and see how it fits with you. It's not mathematics for the sake of calculation. It's mathematics for the sake of thinking about how ideas are related to one another. So the term, a form re-enters its own indicational space, is well exemplified by a Mobius strip, because the re-entry doesn't take it back identically, it takes it back with a twist. And so something new happens here. And what happens in the case of the topological strip, of course, as you know, is that this strip has one edge and only one side, because as you move around the strip, you end up coming back to the other side when you go all the way around it. Probably everyone has made a Mobius band out of paper, and I was going to bring some demonstration just for the sake of that. Maybe in the break I'll go get my scissors and tape from upstairs. But there are some curious aspects here in that the Mobius band is only globally a Mobius band. It isn't locally any kind of a Mobius band at all, right? If your vision was only this much and you didn't see the rest of the band, if all you saw was more or less this arena in here, then it would be an ordinary strip. It's not a Mobius band. It only becomes a Mobius band when it's brought all the way around and twisted and brought and connected into itself. But where did that happen? If you made it, it would have happened at a very specific place. You took the strip of paper, you twisted it, and you pasted it here. But once it's seamlessly pasted there, there is no location for where it became a Mobius band. Locally anywhere, it's an ordinary piece of strip. But globally, it is entirely different from an ordinary piece of strip. So that local to global relationship is characteristic of systems that are reflexive, in that once they become reflexive, they acquire certain global properties which were never there before. They're only there at the point when the self-reference occurred, at the point when the system came back on itself. And you might compare this with other aspects of things like logic, where you could think of the distinction between a thing and its opposite, but in this wider arena, the thing and its opposite turn into one another somewhere in the larger Mobiosity of the situation. So it's a topological thought that L equals not L, the liar paradox, I am not what I seem, or I am lying, or I am simply not what I am, that paradox is not perhaps a paradox at all, but a kind of turn of something into its opposite that occurs when you look more largely at a situation that, that you had been focusing on in such a way that there was a distinction. And it's a way of talking about the fact, I can speak more prosaically, it's a way of talking about the fact that whenever you make any distinction at all, it isn't really always a distinction. It's only a distinction for you, very clearly this or that, in some particular domain that you know about, and as you move towards the boundary of that domain, then it's not clear anymore whether it's a this or a that. Where does your identity turn into the world? And in fact, that metaphor of identity and world was used by, has been used by some people in relation to the Mobius band. Let's go back to the Bayer Mobius for a moment. Jacques Lacan, in some of his writings, talks about this in relation to self and world, I believe. I may have this story distorted. A laser pointer would be nice, but do I have one? I think I have one. I think Najib gave us all laser pointers. Yeah. In the Mobius band, you can walk around the center strip of the Mobius band, and that's a single circle, and you come back to exactly where you started, right? A unitary self. I'm playing with Lacan's metaphor. But if you were to move off from the center circle just a little bit and start walking, then what happens to you? You're down on the bottom of this, and you go through the twist, you're up on the top. And you continue around, and now you're down on the bottom, and you're up on the top. I'm perhaps, this would have been better illustrated if I had actually, what I'm saying is better illustrated out here at the edge of the band where you see. I start here and I start walking, and I'm down at the bottom, and then I continue along the bottom, and I continue along the bottom until I get back to the top, and I have to go around twice in order to come back to where I started, right? If I perturb the center core circle just a little, then what happens is that I start walking along the edge of a putative Mobius band, and as I come around, I come down below, right? And then I have to go all the way around again before I come back to the top, so that it's very unstable at the center of the Mobius band, that core circle. If you perturb it just a little bit, it doubles and becomes 2 times around the band. You started to say something? You understand, yeah? Okay. So Lacan used that as a metaphor for the self and world, because you see this, we tend to split into an observer and an observed world. We tend to take that unitary whatever it was and make a story that says, well, there's the world out here and I'm over here, and I'm separate from the world. And that's the local view of the person who is not looking at the whole band, but actually it's all connected up. And the Mobius band amplifies that metaphor, if you wish to have it amplified, right? So there are lots of aspects of the Mobius that are interesting. Of course, the other thing is that you're not, if you think of outside as one side of the band and inside as the other, then the outside becomes the inside and the inside becomes the outside, and these are, it's the same. But you can play with this in lots of ways. It goes beyond two-valued logic. There's a cyberneticist, I think that's my next slide, yes, Ricardo Uribe, gives this example of design. You might wish to design a simple engineering circuit consisting of n switches, each one of which controls one light. It's a well-known problem, which is solved in one way or another in every building in the world by now. That you have a switch which controls, say, the light over here at the entrance to the building from every floor of the building, right? How do you make that? Well, you can write down the logical, having been trained by Claude Shannon and all the people who descended from his beautiful insight that you can translate Boolean algebra, you can translate two-valued logic into circuit design, because switches are either open or closed, 2 states. You can write down a set of equations for this in logic and translate them into circuits, and then you'll have a big and complicated circuit, which you will need to simplify. But Uribe illustrates that one could have, and perhaps someone did, I don't know the history of the design, make a leap beyond thinking in terms of Boolean logic by having designed a two-line switch of this sort, which has two states. Either current can run along the two parallel lines, or the switch is pressed, in which case current runs from the lower line to the upper line, and from the upper line to the lower line, a cross switch like that. If you think of playing with that, you have a better chance. But then if you have the brilliant idea of thinking about a Mobius band when you saw that crossing, you would solve the problem at once. Because if you put a Mobius here into the circuit, then you see the light is on. And if you put a non-Mobius into the circuit, the light is off. So we're done, because we can put n of those switches along, and then if an odd number of them are pressed, why then you'll have a Mobius, an odd number of twists, and the light will be on. And if an even number of them are crossed, then you won't have a Mobius, and the light will be off. And each one individually controls the light. And if you happen to like to play with Boolean algebra, you can ask yourself, where in the course of designing it using Boolean algebra is this going to occur? And it will if you think about it very carefully, but it won't occur in an obvious way, because the global nature of this way of thinking about the design is not so easily present when you analyze down to the individual parts. So it's a beautiful example of how a design idea might well go way beyond analyzing into logical parts. But that doesn't obviate using the analysis, of course. I'm playing with this a little bit. Here it's not a Mobius anymore, but just a torus. And in the case of a torus, it's the same situation, isn't it? That you have a distinction that you apparently have made. You drew this circle around the band around the meridional direction of the torus, like that. And then if you aren't looking globally, then you have the outside here and the inside over here. But if you look globally, you find that the outside is actually the inside, and so I don't actually have a distinction after all. I only have a local distinction. If you work with surfaces, then this is always a consideration. I think I ask you to simply ignore the symbolism at the bottom of that slide. I'll come back to that. But I wanted to spend just a few minutes talking about a descent from Boolean ideas. What we just talked about was you might say an ascent from Boolean ideas. That is, if you let go of that notion that everything is two-valued and that you're going to be dealing entirely with the analysis of the distinctions you've already made, then you may take a wider view and see how things are related in a way that goes beyond them. And that was what I was just talking about. But here, George Spencer Brown did something else. He descended into something that is more whole, that's underneath the Boolean, by letting go of certain distinctions. It's not different from what I said, but it's a little different from the way we usually think, I think. So this is a depiction of what George Spencer Brown did. I'm talking about George Spencer Brown, who wrote a book called Laws of Form. And you may or may not be familiar with that, but that's the title of the book, and it's about the fundamental notion of distinction. So here I have a distinction, namely this curve in the plane. And if I'm in the plane, it's like I was in locally on that torus. There really is a distinction between inside and outside. You're not going to get from outside to inside unless you left the plane and came back like that, and that would be more like being on the torus. And if you were describing this in an ordinary analytical way, having obtained the distinction outside and inside, you could say that if I cross from the outside, I'm inside, and if I cross from the inside, then I'm outside. And I'm using this angular bracket to mean I cross from, all right? I cross from whatever is inside the bracket. Sometimes in Boolean algebra, people use a bar to indicate not, and I'm using an angular bracket to indicate something similar. But suppose that you took that situation where you have names for everything, and you allowed that maybe I wouldn't have names for everything. I'll just have enough names to elicit the distinctions that I need and not any more. So I don't need a name for the inside if I already have a name for the outside. So the story goes. I won't name the inside, and then I'll know that I'm inside when I'm in the place without any name, all right? So then we have what's on the upper right. And now the outside is labeled O, and the inside isn't labeled, and the equations changed a little bit. Now we cross from the outside and we get to the unmarked place, and you cross from the unmarked place and you get to the outside. And in the behest of parsimony, why should I keep on using the symbol O when the cross itself with nothing inside it seems to be serving the same purpose? So I will divest myself of a little more notational clothing and remove the O and replace it by the symbol cross. So now the symbol cross means two different things depending on the context. It means cross from the unmarked state, and it means marked or outside. Two things. But you can tell by looking at the context which one you're in. So we have, this is the name of the outside, the name of the inside is unmarked, and crossing from the marked state, crossing from the outside, takes you to the unmarked state, the inside. And the mark itself makes a distinction. Remember, I'm divesting myself of unnecessary mathematical clothing. So the mark itself is making a distinction between its inside and its outside. So why don't we get rid of the distinction itself and replace it by the mark of distinction? And then we have this situation where the mark of distinction is carrying its own name on the outside, like I carry my name with this name tag. But I don't need the name tag. But maybe I should keep it on anyway for the purpose of formality. But I don't need it. So that becomes another equation, namely the mark with its name tag could be replaced by the mark alone. And you end up with two equations about this one symbol which makes a distinction. One equation is that if you put the symbol over itself, then it vanishes. And the other equation is that if you put the symbol next to itself, then it condenses to one copy of the symbol. And you've seen the story that puts some meaning on these two equations, which could have been presented to you in an antiseptic logician's way as two equations about a certain system of symbols which we will manipulate. But I didn't do that. And we have interpretations here. The interpretation of this one is that if you cross from the marked state, you're in the unmarked state. And this one says that if you call the name of the marked state in the presence of the marked state, it's the same as having the marked state. Or if you call a name twice, then you get the name, as far as names are concerned. Yes? I'm not quite sure what you're saying. Where are you? Here? Second row, yes. Yes.
So one of the markers, say from outside you're coming inside, and then again you're crossing over now from where?
I'm not quite sure what you're asking me. If I cross from this state, I end up in the unmarked state, right?
Now that second marker again, then are you not going out again?
And if I come out, then I cross from the unmarked state and I end up at the marked state.
What do you mean by two of those?
Two of them means that I cross from, let's go back to where we came from. Crossing from the outside is taking us to the inside. Crossing from the outside is taking us to the unmarked state. But then I followed a pun, because in this equation, once the inside had become unmarked, I found that the notation cross all by itself with nothing inside seemed to be being set equal to O, the name of the outside. I can use just the cross as the name of the outside. So then cross over cross means cross from the marked state. So let's take it literally, right? Just read it. It says cross from the marked state. Here's the marked state. Crossing from it, I end up in the unmarked state. Another way of reading it would be cross from the unmarked state and then cross again, right? Twice. Starting all the way inside. It would be twice. It would say cross from the unmarked state, then cross again. That's all right, too. Cross from the unmarked state, and then cross again, and I'm unmarked.
If you cross from the marked to the unmarked and then back to the marked.
Right. So I could cross from the marked state to the, maybe we should illustrate on the, so if I started in the marked state and I crossed to the unmarked state, and then I crossed backward, I would end up in the marked state, right? This is all this, we're just thinking about this very simple situation and watching how the language of it works. Because if I started in the marked state, that's where I am here, and I crossed from it, I would end up here, which is the unmarked state, right? And then cross from that again, I would end up back here, like that, right? Every time I cross, I put a marker over it. But two of these is none at all, and so that's the marked state again. Once we have that this is nothing, well then that will keep track of the number of crossings modulo 2 as it should, right? The mathematics is very simple. It's just modulo 2 mathematics combined with condensation mathematics, right? And the calling of a name twice. Nothing very complicated about the mathematics itself, but there are some conventions here. And but the thing about it is that once we made that descent, then this became a distinction in itself, and it also became a name, and it also became an operator. So it became something like a noun, but it also became something like a verb. And it became something like an actuality as well. I'm sorry? Is it time to change the... Okay. This is a... Let me say one more sentence and then we'll stop. So you see that we've arrived at a reflexive situation here by taking the descent that Spencer Brown suggested to us. We have arrived at a situation where, by condensing the language, we have found that the actuality and name are so close that you can't really distinguish them if you don't want to, and that name and action are also so close that you can't necessarily distinguish them unless you want to. Name, action, and actuality are all one. Concept and what we call reality are not separate. And we came to a point of fusion or a nexus from which we could go outward again. And this is different from saying there is a large arena and it has it re-identifies things that we had made different, or is it? Well, or rather, I may be misinterpreting what you say, but it's something that occurs to me to say. That you can tell me, but I delineate two arenas, and in those arenas you're allowed to say yes and no, or marked and unmarked. You're allowed to say these things. So one might, in the unmarked arena, walk in and put in a mark, and then suddenly all these conventions go awry, right? Because a mark has been placed in the unmarked arena. So this is a little delicate. We have to make a convention. There is no mark in the unmarked arena, and so on, right? If we start putting the language into another language, right? So that of course always happens. You say no, I say yes, but maybe actually I meant yes by my no, and maybe actually you meant no by your yes. Because as soon as multiple languages start to interact, the conventions may be actually quite different. So in speaking about this dissent, the difficulty in it is in asking you to accept precisely these conventions for divesting ourselves of mathematics, mathematical notation, and then to see the insight that you get from that. And many people I've talked to about laws of form, they know that he said that, but they would prefer to say something else, and they have another slightly different insight as a result of saying something else. I could mention some. For example, some people, I think Ranulph likes this, is to think of this as being a bit incomplete, that really what's happening is that the boundary itself is more like a Mobius strip, so that even when you cross the boundary, you're actually on the outside if you looked at it from the point of view of the Mobius. So there never was, right? And you're understanding that the distinction is only the one you built. But lots of different ways of thinking about it. What was radical from the point of view of Boolean algebra was the idea that, I'll write it on the board. You see, you had two states, right? Which I'll just write as this for unmarked. This was marked, and this was unmarked. So this might be the same, this might be true, and this might be false, right? Two states. You might interpret it that way. And then you would have that if you put a mark over true, it would be false, and if you put a mark over false, it would be true, right? And so it begins to look like ordinary Boolean algebra. Now we're going back up the condensation. But then the mark stands for one of the truth values, but it also stands for negation. That's kind of strange from the point of view of Boolean algebra, which had carefully, or logic, which had carefully separated negation. Negation from the point of view of the way we were all inculcated into logic. Negation is quite separate from the values of true and false. Not here. Not here. What you have when you have the marked state, when you have the mark, is you have the mark, and you have, as a result, the distinction that it made, which gave you an inside, and another side, which is the outside. So you have a triplicity, which is a single thing. You have a trinity, which is one. Not that I'm making any religious comment at this point, but that's what you have. And the idea that you could have just a separate value, true, and another separate value, false, is an extra distinction that is being made out here in language about this situation. I'm not trying to do this with fuzziness, although fuzziness is a lovely approach. But fuzziness uses more distinctions, and I'm trying to use fewer, right? So with fuzziness, we can talk about how far in we are. We are 90% of the way in or out, but that's another matter. That's really another matter. I like that. perhaps enough said about this, except the main point I wanted to make was that by making that descent, you actually are coming into a reflexive domain. The mark stands for distinction, and so is talking about itself, right? You have gotten to a self-referential point when you use this that isn't in ordinary logic directly. It's only implicitly in logic that this self-reference is occurring, and that the name and the operator are sharing each other in the language. And what Spencer Brown discovered, which is quite significant when you think about it, is that it all works just fine with this tiny language, which just uses one symbol, which is allowed to be inside itself or next to itself. So you can play with that language irrespective of these interpretations that we put on it. In our descent into simplicity, we deliberately ignored the boundary, right? We didn't assume that the boundary had any meaning. In fact, we were willing to just replace it with a symbol, right? In the case of the symbol is something where the boundary state is being ignored entirely. I don't care about living on the mark itself. Not yet. Maybe that's an extra distinction I could think about. I'm only concerned with marked or unmarked, right? I can do that, right? I can do that in the English language, at least. But then, sure, why shouldn't we think about the boundary? If you start to think about the boundary, how are you going to do it? It might be then that you are approaching something like fuzzy logic by degrees, right? There would be the state of being outside and the state of being inside and the state of being on the boundary itself. So you may wish to amplify the boundary. One way you could amplify the boundary would be to say, well, really the boundary, the boundary circle, it's really a Mobius band. It's neither inside nor outside. Sometimes when you look at it, it points to the outside, and sometimes as you move around it, it points to the inside. It's neither inside nor outside. Or another way of thinking about it would be that it's really the self-referentiality of the boundary that you're talking about. That here's a geometrical line boundary, and the outside, when you're away from that boundary, is designated by marked, and the inside is designated by unmarked, right? Which I write a symbol for because it's very laborious to keep pointing to nothing. It takes a lot of energy to point to nothing. But what about the boundary itself? Well, the boundary itself could be, for example, you could decide that it would be named by the reentering mark, right, as a third value. Neither marked nor unmarked, but the place where the thing turns on itself. And then you have a picture that is leading towards the fuzzy logic or the multiple valued logic, where the boundary is obtaining a new value that's neither marked nor unmarked. All right? That's one possibility, and it fits in this case, both in its circularity and because the reentering mark has the property that it is sitting inside itself like this, right? That's what it meant to be reentering. It sits inside itself if you took it literally. I used it at the beginning without saying anything other than it reenters its own indicational space. But if we took it literally, which of course is making another distinction, then it sits inside itself, but then is it marked or unmarked, right? If it were marked, why then, according to the equation, it would be unmarked. And if it is unmarked, then according to the equation, it would be marked. So it's neither marked nor unmarked, the reentering mark. The reentering mark is a third logical value, a tertium non datur, something else, something outside of the distinction between this and that. So by following the metaphor of geometric boundary, you arrive at that in a neat way. But you might want to say something else. You might well want to say, I'm considering multiple distinctions, and I want to think about what percentage of one of them, let's say, love and hate, right? And love and hate are opposites to one another, perhaps, but in a real situation, I love you this much and I hate you that much. Maybe I could almost quantify it. And then it becomes a point in a plane of love and hate. And I would use a different representation entirely. And the boundary arena has been multiplied, has been opened up into an entire two-dimensional space for the two parameters of the two sides, right? This is perhaps fuzzy, but I don't think of it as fuzzy. It's just how you amplify into the boundary is very creative possibilities. So as soon as you go away from the situation of very, very simple distinctions, then it becomes complex. It does. Some boundary situations, it's completely clear what you would say is the boundary. The boundary between the inside of a circle in the plane and the outside is a circle. But what is, even in mathematics, what's the boundary between finite and infinite? Or even, what is the boundary between 1 and 2? There is no sharp boundary there. But we intermediate between 1 and 2. Are you saying you're interested in seeing what we might do to model more complex boundaries? Yeah, sure. So am I. I'm interested, but I'm not sure what the best answers would be. It depends on the situation. One way to do it is to respect the topological situation more carefully, just as we would here. That is, the boundary is actually described in the mathematics if we were to think of it as curves in the plane. And more generally, I can talk in a wider topological language about points that are in the boundary of some set. So one can do that. One can think about the shapes of boundaries. There are lots of things you can do with boundaries. But if it's not boundaries, if it's relative modalities, then you want something else. So it all depends. And I'm focusing on the simplicity, not the complexity here. Okay. Well, let's continue a bit. I put this in here without any explanation so that I could talk about it a little bit. It has to do with all, rather, so I've gone back to all rather than almost nothing. And if you try in language to talk about all, like all possible collections of things, all sets, that's Aleph. Aleph is the set of all sets, the set of all possible collections. And if the problem with it is, if it be a problem, is that it won't stay still. As soon as you have it, you think you have it, the list of all possible things, you made another thing, namely that list of all possible things. And so that has to be taken in. And so it never stops. It's always a little larger than itself. P of Aleph meant all the subsets of it. Every time you take any part of it, you have to put it back into it, and it won't stop. So it is an always growing self-referential thing. I just wanted to mention it in contrast to this, to the extreme simplicity of trying to get down to just one distinction. But you noticed what happened when we tried to do it. We could play the discussion farther, and it would do it again. You tried to go down to just talking about a single distinction, and immediately, or even no distinction at all, and immediately we start bringing up all of the different complexities of distinguishing that we're familiar with, and all of the ways of creating things that we're familiar with, and all of the ways of creating things that are kind of potential to us. So we really can't stay still and just dwell in no distinction at all. We're not built that way. If we want to contemplate it, we have to take a descent and see what happens, and then watch what happens as it boils up again, and so on. At least that's my experience. So that's the way it is. But the self-reference is not just out here in language, figuring out ways to refer to something that's already there or have something refer to itself. That's out in the complex part. The self-reference is also down in the bottom, but it's more delicate. It's like the core circle in the Mobius band. As soon as you perturb it a little bit, it wants to become two. This is another quote from Heinz von Forster. Laws of physics and so-called laws of nature can be described by us. The laws of brain functions, or ever more generally, the laws of biology, must be written in such a way that the writing of these laws can be deduced from them. That is, they have to write themselves. But we're not there yet. And I would like to see physical laws or scientific laws somehow coming out of just the act of attempting to make laws altogether. And sometimes you can do this with 20/20 hindsight, but it isn't so easy or even obvious that it's possible for human beings to do that, to write the laws directly from nothing. So trying to go down that descent is very interesting for exactly that reason. I was going to skip this, but we could say a word. If you write A mark B, then this is A implies B in logic with the interpretation that we mentioned. And so you're actually, you are constructing everything you need. This is A or B. And this, which looks a little complicated, is A and B. And there's nothing mysterious about that. I just didn't want to, you can see what I'm saying. In terms of marked or not, right? How could A, B be marked? Well, what are the possibilities? You could have A marked and B unmarked, or you could have A unmarked and B marked, or you could have them both marked. And in this case, this will be equal to marked, and this will be equal to marked, and that will be equal to marked. So, but in the remaining case, where they're both unmarked, it remains unmarked. So if you put two next to one another, then the only way that it can be marked is if one is marked or the other is marked or both of them are marked. So that's or. That's A or B. So this is A or B. And then if you look at this one and try the same thing, you'll find out that the only way it can be marked is if they're both marked. You see, if they're both marked, we're doing some little exercise here. Suppose they're both marked. I'm looking at this one now. If they're both marked, then you see that the double marks go away and you have unmarked state and you have marked. So then it's marked. But if either one of them was unmarked, then you would have a situation like this. A is unmarked, B is marked, and we put a cross over the whole thing. Then this goes away. Oh, but then it all goes away. So it won't be marked unless they're both marked, and you get and. And is A and B means they're both marked. They're both true. That's the only way it is true. So there are other, I'm showing you some other images now. Like the image, Escher's beautiful image of hands drawing each other, right? And this is a very compelling image for a number of reasons. We know that we are systems that can act on themselves, right? And we know that our thought acts on itself. And yet, when we try to represent such a thing, we find that we can only represent it in an imaginary way, which is very peculiar, or we run into logical paradoxes, like the liar paradox that we had before. That in attempting to put into language something which is very real for us, we end up with this kind of curious, very vivid imaginary illusion, and in the illusion that Escher has created, it seems very real that, and I'm using these words real and illusion, and they need to be examined, that the hands really are drawing each other. But then we know that it's actually done on the substrate of the paper, and it's simply an illusion. And some people, for example, Douglas Hofstadter, who likes this kind of imagery, some people take the stance that that's exactly what it is, that it's an illusion, that the state that you have, that you are familiar with, of your world is a hallucination that is hallucinating itself. It's an illusion. Some people take this stance. Other people take this stance as well as Hofstadter, that it's an illusion created on a substrate which has nothing of that, but somehow that substrates of that kind are capable of bringing forth such an illusion. I'm not saying that that's the answer. I don't think so, but I don't know what the answer is. And people take definite stances in places where I think there's a multiplicity of views. And of course, an artist like Escher is standing in the multiplicity of views and knowing full well how he made it. Here's the logo of the ASC, its new logo, the American Society of Cybernetics. This is a knotted curve. So it's knotted, but it's actually a rather interesting knot that everyone perhaps knows very well. How much do I need to do here? Yes. So let me see. There we go. Like that, right? It's sometimes called a square knot when it's made into a knot. But what you have are two loops, right? And each loop catches the other loop. So they mutually catch one another, and as a result form this bind, which will not go away. Of course, it can go away if you unthread it or unknot it, but it doesn't go away as it stands. There it is. What? Same, like that. Right? Upper loop, lower loop, and then this is connected in the logo. This is connected, and this is connected, so it comes around like that. Yeah, that's the way that logo works. If you think of it and elongate some parts of it, I'll just put this inside my hand like the magician does to hide it, but not for the sake of a magic trick, but just to make it a little more vivid for you. Then this is also, if you connected it up here, then this would be the logo, right? And so it looks like a snake with two ends. This is one end of the snake, and this is the other end of the snake, and its snake is biting its tail. It still looks like the old logo, which was something like this, a snake biting its tail. It's a more modern topological version of the same. But you see that this is an example of, like the Escher hands, but a little more concrete, of neither of these loops by themselves create the bind, but together they do, and they really do. So we crossed the boundary from it being purely imaginary to being quite real. What happened? I'm never quite sure about that, because you see there's still a double level, right? There's a double level in the Escher drawing between the hands and the substrate out of which they're built, and your imagination of the hands. But here there's a double level which has been made physical in that there is the level of the rope, which is not even knotted, and the level of the ropes as they grab one another, which is quite knotted. So what is going on there? And when you make a knot, it's similar. You make a knot and you put a pattern which has a physical stability onto the rope. It won't go away unless I slide it off the ends. But it is meta to the rope. The rope is still the rope, and the pattern has been embossed on the relationship, not on the rope, but on the relationship between the rope and the space in which it sits. And so I think that some of the answers to the question of that reflexivity are lying in the lessons that are in that topology about the knots. So what we're going to do after the break is look at the symbolic and logical epistemology of the knots, starting from a simpler place and ending up more or less back where I'm stopping now. I mean, you're talking about each process is waiting for the other process?
Is waiting for the other process
Yeah.
to free
Yeah.
some resources
Yeah.
that are waiting for the previous process
Yeah.
to free the same
Right, so that's a deadlock.
That's
Yeah.
a deadlock.
Right.
That's a deadlock.
But there are other situations where you make where you design in such a way that processes will come online just exactly in order to promote each other, and that's similar. Oh, sure. No. You understand? I do not claim that you must learn topology in order to solve your problems. I'm merely using a language which has some mathematical simplicity in order to illustrate ideas. Right. By the way, before I forget it, this clasp, which is very ancient, of course, that bit of clasp, was recently, and it's very simple to prove, shown that if this occurs by David Krebs in his thesis a few years ago, if this ever occurs inside a knot, the knot has to be knotted. So this really is a deadlock. I mean, once you looked at some complicated mass of rope all knotted up, if you saw this, you would know that it had to be knotted. It couldn't be undone.